Hello everyone, so in this video we would now be solving for the moment diagram of this particular beam, which we have solved for earlier. So earlier or in the previous video, we have solved for the determinacy, the reactions, and the shear diagram. So again, in this video, we would now be solving for the moment diagram of this particular beam. Okay, so same approach as with last video, wherein we would just be cutting sections at the particular areas of interest and just plot it like what we have been doing in the shear diagram. Okay, so at this particular portion, guys, if you would be cutting a section here, the moment here is actually 0. As you can see, guys, that this is just a pin support and not a fixed support. And if it is a fixed support, meaning that it could have it could have a moment restriction, meaning that it should have moment. But again, since this here is just a hinge, it does not include any moment. Okay, so from that, guys, or let's say that if you would be cutting a section here, the moment there would just be equal to 0. So meaning that for our first point of interest, I will be making use of a red ink. At this point, the moment here is actually equal to 0. Okay? So next up, so in this span here, so if you would be cutting a section anywhere here, you should be plotting the results at the moment diagram. So better yet, I would just cut a section at the last part of this uniformly distributed load. So with that, guys, it would now look like this. Okay. So next up, if I am to get the moment about that particular point, so what I would be doing is just that I would be getting the summation of moment about that point. So since this, I assigned this to be section AA, so I will be getting the summation of moment about that point. And since when I have cut this section, meron po tayong tawag dito, resulting internal moment. So for the ease of computation, whenever you are to cut a section in order for you to plot the moment diagram here, your sign convention when you are cutting a section is that clockwise should be positive. Okay? So meaning, guys, getting the summation of moment about this particular point and getting the this sign convention, you will now get the data that you will be plotting in this graph. Okay? So from that, guys, once again, getting the moment about this point. So what do we have? So we have here the 32.1111 kilonewton force, which is the reaction, times the lever arm of 4 meters. So as you can see, guys, since our convention is clockwise positive, so meaning this must be positive since this force here is causing a clockwise rotation about this point. So positive. Okay, so next up, so we have this particular force, and from that, this force causes a counterclockwise direction. And from that, since our sign convention is clockwise positive, this must be negative. So negative what? So we would be getting the resultant of that force. So in order for us to get the resultant, so let's say that this is the resultant here. So the location of the resultant is acting half of it. So this is 2 meters. And this also 2 meters. And for the resultant, that is just the total area of 10 and 4. So that this is 10 kilonewton per meter divided by, times 4. So that is 40. So from that, this is 10 times 4. But take note that this is just the force. We must multiply it by the lever arm. And what is our lever arm? So the lever arm is the distance from this point up until the location of the resultant, and that is 2 meters. Okay? So just multiply this by 2 meters. So from that, guys, we can now solve for our first point of interest. So for our first point of interest, that is 32.1111 times 4 minus 10 times 4 times 2. Okay? So our answer here is positive 48.4444 kilonewton meter. Okay, so going back to our graph here, in order for us to plot it. So again, it is positive 48.444. So I would approximate it to be located at let's say this location. So if I am to draw a line here, so at this line, the moment here must be 48.4444. Okay, so the next issue here is that how would we plot the area in between? So this area here. So previously in this section, we have just connected it with a straight line. So if you are thinking that we just um what do you call this? Trace this with a straight line or a straight diagonal line. So sorry to tell you, but that is actually incorrect. Okay. So what is now our basis? So our basis is the shear diagram. So as you can see here, guys, in the loading diagram, if this is horizontal, for the shear diagram, it will now be slanted, but it will now, it is still a straight line, but it is now slanted. But if in the load diagram, this is slanted, so this is triangular. For the next one, it is now curved, as you can see here. So again, guys, this is actually a 1-degree curve. And we would just be adding 1 to that in order for us to get the degree. So this is now a 2nd-degree curve. Meaning that it is more curved than that of a 1-degree curve. So meaning, guys, kurbada siya. So this here, as you can see, that it is now curved. And as for this one, guys, this is a 0-degree curve since it is horizontal. And if you were to add 1 there, this is now a 1-degree curve. So meaning, guys, following that logic, the curve at the moment diagram, this should now become a 2nd-degree curve. Okay, so for that 2nd-degree curve, our next issue, will it curve this way or will it curve this way? Okay, so once again, our basis is that of the shear diagram. Okay, so in here, guys, as you can see, that at this particular point, at this point here, the shear here is a positive value. Meaning, guys, that the curve here, the curve that is acting at this location, the first point of it has a slope that is upwards. Okay, so since this is positive, its slope is upwards. So it might be like this. Okay, as you can see, it is upwards. And as you can see at this particular portion, the slope here is, or the value here is negative. So meaning if it is negative, it means that its slope is going downward. So meaning, guys, it must be like this. Okay, so if I am now to trace it in that direction, so upwards, so it is once again upwards, then it will now slope downward. So this is now the curve. Okay, so if you can remember from earlier or from the last video, that if you are to consider this curve, the value here is 0. So meaning, guys, that at this particular portion, it must be perfectly horizontal first. Okay, so this is horizontal. And as you can see here, guys, that it is, this one here is pointing downwards. So meaning that it must be almost, it is, it must be pointing downwards, as you can see at this curve. And in here, guys, since our arrow, or since it is positive, it must be upwards at this point. And since the value here is negative, it must be downwards at this particular point. Okay, so what about for the next one? So again, following the same logic, let us now cut a section about this point. So this is now our next point of interest. So if you were to cut a section about that point, so it is now this one here. So same procedure, let us just get the moment. So summation of moment, and our sign convention is once again strictly clockwise positive. So for the summation of moment about this point, this is now equal to, so same, 32.1111 kilonewtons times what is the lever arm, that is 2 plus 4, so meaning that is 6. Okay, so in here, for this particular force, so again, this is 10 times 4, or the resultant, and its location is located 2 meters and 2 meters about that point. So the distance from this point to this point, that is 2 meters plus 2 meters, so that is 4 meters, okay? So this is now negative since this force is causing a counterclockwise direction about this point. So this is now negative 10 times 4 times the lever arm of 2 plus 2. So that is now 4. So getting the answer here, looking at the calculator once again, this is 32.1111 times 6 minus 10 times 4 times 4. So this is now 32.6666 kilonewtons. Okay, so there. And it is still positive, so meaning that in our graph, so it is actually located at this portion. Okay, so at this portion. But take note, guys, that this is not a curve any longer. So if you are to check for this particular span, if you are to check for this span in the shear diagram, as you can see that in the shear diagram, it is perfectly horizontal. So it means that this is actually a 0-degree curve. So meaning, guys, at this portion, it must now be a first degree curve. Okay? So first degree curve meaning that it must be a straight line. So plotting the answer of, let's say, this is positive 32.6666. In order for us to connect this point to that point, it must be a straight line. So apologies for what you are about to see. This might not be a straight line. It is very hard to me to draw a straight line using our what do you call this, cursor or mouse tab, I should say. So draw so apologies. So assuming that that is a straight line, again, this must be 1 degree. Okay, so next up, so since we have already plotted up until this point, let us now plot this particular point. And from that, guys, let us now cut a section at this location. Okay, so same procedure, summation of moment is equal to whatever the moment is, and again, strictly clockwise positive. Okay, so looking at our figure here, what forces causes rotation? So we have 32.1111 kilonewtons times what is now the lever arm of this force. That is 4 plus 2 plus 3, 9 meters. Okay, so it is the only positive here since it is the only force that would cause a clockwise rotation. So as for this force here and this force here, they would cause counterclockwise direction or a moment, I should say. So meaning that those must be negative. Okay, so minus, so this here is 10 times 4 once again, or just 40 times the lever arm. So the lever arm from this point to this point, that is 2 meters plus 2 meters plus 3 meters. So that is 7 meters. So I'm kind of having trust issues here. So if I am to calculate, so this is once again 2 plus 2 plus 3. So 7. Okay. So minus 15 times 3. Okay. So getting the answer here. So looking at the calculator, so this is 32.1111 times 9 minus 40 times 7 minus 15 times 3. So the answer here is now equal to a negative answer of negative 36.001, or if I am just to round it, negative 36 kilonewton meter. So with that, guys, in our graph, so it is now located at this portion, which is at the lower part of the graph since it is negative. And as you can see, guys, that for that particular span, so in this span, according to the shear diagram, it is horizontal, meaning, guys, that this must be a straight line. So this is a straight line. Apologies once again, since I'm having a hard time drawing digitally a straight line. Once again, this is a straight line. Okay, so this is negative 36. kilonewton meter. Okay. So next up. Okay, next up. So once again, this is a 1 degree line. So next up, let us now get this moment here, which would comprise of the whole. So the whole beam. So let us get the moment about this point. So once again, summation of moment is equal to, so clockwise positive. So that is 32.1111 kilonewton times the lever arm of 3 times 3 times 2 times 4. So that is, so looking at the calculator, so that is 3 plus 3 plus 2 plus 4. 12. So we have here 12 meters. So minus, so for the resultant here, that is 40 or 10 times 4 times the lever arm of, so if this is 2 meters, that is 2 plus 2 plus 3 plus 3, and that is 10. So that is 3 plus 3, that is 6, plus 2, that is 8, plus 2, that is 10. Okay? So minus 15 times, so the lever arm of 15, that would be 3 plus 3, so that is now equal to 6 meters. Okay? So what else do we have here aside from the value of 15? You also have RB of 40.889. So plus this time because this force here would cause a clockwise rotation about this point. Okay, so plus 40.8889 times the lever arm of 3 meters. So do we still have more? Actually, we still have more. We still have this force here. So for this force, this is equal to 1/2 of 12 times 3. Sorry, 1/2 of 12 times 3. So from that, and as you can see that it causes a counterclockwise direction. So this must be negative. So negative 12. Sorry, negative 1/2, I should say. So negative 1/2. 1/2. 1/2 times 12 times 3. But take note that that is just the resultant here. So the lever arm here is, so if you would be measuring from this point to this point. So let me just erase. I think our board is getting messy. So from this point to this point, the location of the resultant, that is now equal to 1/3 of the length, and that is equal to 1/3 of 3. This is now equal to 1 meter. So the lever arm here is 1 meter. Okay, so getting the answer here. So 32.1111 times 12 minus 40 times 10 minus 15 times 6 plus 40.8889 times 3 minus 1/2 of 12 times 3. So our answer here is actually 0.0001, or this is approximately equal to 0. Okay, so in order for us to get a correct answer, as you can see guys, that in our, so that is, in here, in our figure here, we do not have a fixed support here. So meaning that the moment here should be 0, which is of course correct in our assumption. So in this point guys, in this point, it is perfectly equal to 0. So meaning that our shear end moment diagrams are correct. So next up guys, how do we connect this? So how do we connect this point to this point? So once again, we would be basing it from our shear diagram. So in our shear diagram guys, so in this part here guys, it is a positive value. So meaning that it would be, the slope would be kind of pointing upwards. So meaning guys, so for the slope, it is near vertical. So let's say that I will be slanting it that way. And at this point guys, at this particular point, it is 0. Okay? So it is 0. And since it is 0 po, so since it is 0, at this portion, it must be perfectly horizontal. So if I am to trace that, so it must be like this. So if I am to trace it with my laser pointer, it is going upwards, then it would now be reaching a slope of 0, or it would now follow this path upwards, then horizontal. Okay. So once again, apologies for what you're about to see. So this is now my drawing. So upwards, then, oh, sorry. Then it is approaching a horizontal line, but let me just do that again. So upwards, then horizontal line. So this is now our moment diagram for this particular beam. Okay. So lastly, let us now draw the deflected shape. Okay. So for the, wag na po na.